Hey, welcome back. This will be a short video. What you're seeing in front of you is a 10 megahertz oven controlled oscillator. I bought a few of these on eBay several months ago, and I was hoping to do a quick test with them to see if they are putting out 10 megahertz and if there's any way for me to fine tune or tweak the performance of these units under test. And I finally got around to it, so I was hoping to maybe do this short video to kind of demonstrate that. Before we go in, I just want to give you a quick look at the data sheet, and let's see if I can get a view of that. It's fairly straightforward, to be honest. There's the VCC and the ground, pin 5 and 2 respectively. The pin 1 is the output. Pin 4 is not used. But there's a way to tune or tweak the performance of the unit by connecting a variable resistor of some sorts between Vref and VCC, and then make it perform or closely match a certain frequency, if you will. In this case, I'm hoping to do so by hooking up a variable resistor I built some time ago. A couple of other points that are important for this experiment is really the requirements of the voltage and the current. They are supposed to work at 5 volts, and I've seen these units work much better actually at 6 volts. Maybe the units I have some sort of a flaw and therefore deviating from this data sheet. In any case, and they also require about 600 milliamps when the unit first starts to heat up. Obviously, these are oven controlled oscillators, which means the oven has to heat up at the startup of the unit. Once they reach a certain temperature, they stabilize, and then they start to go into the stable state, and at that point they use anywhere between 250 milliamps, somewhere in the range of that. Again, this is a very straightforward unit, nothing fancy going on here. I'll link to this data sheet in case you guys are interested. I also want to quickly cover the output on my oscilloscope. The channel 1 is this yellow plot here. That's fed by my HP 5334B as in Bravo. It's a universal counter, but the one I have has a built-in oven controlled 10 megahertz standard, and so I'm using that as a reference for this particular experiment. So the top one is putting out 10 megahertz, and you can actually see here, let's see if I can do a quick zoom. You can see the frequency 1 in this case. It's putting out roughly 10 megahertz. And then the bottom, the blue plot here, is fed by the device under test. It's hooked up to channel 2. Now, it's the frequency is showing as also putting out 10 megahertz, but there might be a little bit of a deviation from the channel 1. So we'll figure that out later. But and therefore, there's a reason why the lower plot is straying around from the channel 1. Let me talk about how I'm hoping to kind of get this in lockstep with the channel 1. And the one way to doing that is, as I was sharing earlier, connecting a variable resistor between Vref and the VCC, and then figuring out what value of the resistor will help it get closer to the reference channel 1. If you recall, some time ago, I built this guy here. So this is the variable resistor I built using these Thumbwheel switches. You can watch that video, and I'll put a link to it. In any case, this comes with 2 leads, And these two leads, one of them goes to the VREF on the device under test, and the other goes to the VCC. So let me hook this up and I'll be right back. Okay, so I hooked up the variable resistor stack, otherwise known as Decade Resistor, to the device under test. While I work the Decade Resistor, keep a close eye on this background plot. Our goal is for this to slow down and get in lockstep with channel 1. So I'm going to see if I can reduce the value. It's, well, higher numbers are making the graph go faster. I'm going to reduce it. Reduce 4, 3, slowing down to 1, and let's see if we can reduce this down. 6, 5, 4, 3, 2, 1, 2. So 1's now going in the opposite direction, which means I need to increase this just a tad bit. So as you can tell in the background, it is still wandering about. So I'm going to increase or decrease. Nope, I need to increase. Let's go up, 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 slowing down, up. It's moving ever so slowly, so I'm gonna, so it's moving that way now, so I'm gonna reduce this, reduce one more. So that is now almost locked into place, kinda. With these values, again, I don't care what these values are for now, at least. I think all I'm trying to demonstrate here is the Decade Resistor can be super valuable when you are experimenting with scenarios like these, where you need to quickly put something together to test the tuning or fine-tuning of your device under test, in this case the Oven Controlled Oscillator. The reference standard and the device under test are in lockstep. Both of them are measuring about 10 megahertz, very close to each other, which is great. And according to the data sheet, it's 5 volts and it's roughly 0.17 amps in a standard stable state. Seems to be working fine. So I'm quite glad that the Decade Resistor, or this variable resistor idea, is definitely useful, especially in scenarios like these. I hope this was valuable, useful, or at least intriguing. Thanks for watching. Till next time, take care and God bless.